We're going to go over the quiz here so we can see how to do this, because there will definitely be questions like this on the test, which, by the way, is tomorrow. So, first one, you can, if you imagine this two just kind of hanging out, the real issue is what happens to this absolute value x minus 2 over x minus 2. So, of course, if you just stick 2 in there, you get 0 over 0, which is indeterminate. So we have to try to think what's going on. So the idea here is if you approach 2 from the left of this function, so if you plug in something like, say, a 1.9, then you would get a negative 0.1 in absolute value over a negative 0.1 that's not in absolute value. And so that's going to end up being negative 1 times the 2 is going to be, this is going to approach to negative 2. So that's our left-hand limit. And the right-hand limit, the limit as you approach 2 from the right of this function. So imagine plugging in 2.1, and you're going to get the absolute value of 0.1 over 0.1, which is just 1, times the 2. So our left-hand limit is negative 2, the right-hand limit is positive 2. So since the left-hand limit is not equal to the right-hand limit, you say the limit does not exist. So don't forget to say that it doesn't exist, DNE. Okay, the next one, if you directly substitute in 0, you again get 0 over 0, which is indeterminate. The trick here is to rationalize the numerator. So we're going to multiply top and bottom by the square root of x plus 4 plus 2. So in the numerator, that's going to give us the difference of 2 squares. Removes the radical x plus 4 minus 4. In the denominator, we will patiently wait. Don't distribute, you just make a mess out of things. And so you can cancel the 4's. Once they're out of the picture, then you can cancel the x's. And now we have just 1 over the square root of x plus 4 plus 2. Now we can take that limit as x goes to 0. Since the square root of 4 is 2, we're going to get 1 over 2 plus 2, and so the limit is 1/4. And I should have done this one next time. I missed that. So I'm going to come back to here. Again, if you plug in 0, we get 0 over 0, which is indeterminate. So what we want to do here is we need for this 4x to match what's down here. So you can either pull out the 3 halves and put in what we want, or you can leave the 2 and multiply it by what we want. So I think I'll just pull it out. You don't have to do it quite this way. So now what we need is to make that be 4 so that these can go to 0 at the same rate. So we'll multiply by 1 in the form that we want and move this 4 into the denominator. So now as x goes to 0, these are going to go to 1. That's a limit that we have to know from memory at this point. And then you're going to get 1 times 3 halves times 4 is going to be 6. And so that means our limit is 6. So on here, the question here is it A, continuous, and B, differentiable? And so the continuity piece is we're going to plug in 0 here, and that's going to be 1. So that is going to be our left-hand limit. And if we plug in 0 here, we get e to the 0 is also 1. That's both our right-hand limit and the value of the function at 0. And so to be continuous, we need for the limit to exist and for the function to be equal to that same thing, which it is. So yes, it is continuous. Now we need to be differentiable. We need to take the left-hand derivative and the right-hand derivative at 0. So here we are to the left. So the left-hand derivative is going to be just 2, no matter what you plug in for x. The right-hand derivative, if we differentiate this, is going to be 2e to the 2x. When you plug in 0 there, you're going to get e to the 0 is 1 times 2 is 2. So since the left-hand derivative is equal to the right-hand derivative, and it was continuous, then yes, it is also differentiable. Let me clear some space here. So same question on the next one. And so first the continuity question. Oops, I erased what I didn't want to. So on the continuity question, when you plug in 0, you're going to get that the left-hand limit is equal to sine of 0, which is 0. The right-hand limit is going to be -1. And since our left-hand limit is not equal to the right-hand limit, then the answer is no, it is not continuous. So then without any more work, it can't be differentiable because it has to be continuous before it can be differentiable. So we never even get to look at the left-hand derivative and the right-hand derivative, which is good because otherwise you would be misled, right? If you do take the derivative here at 0 and the derivative here at 0, they'll be equal to each other. But because the two curves are not continuous, I'm trying to think what that's going to look like at 0. So you've got a sine curve coming in here, and you've got the 2x minus 1 coming in here. So their slopes of the tangent lines right here are going to be parallel to each other. But because they're discontinuous, that's not differentiable. Okay, and then this we're supposed to find f prime of 2 using the definition of the derivative. So definition of derivative, you can do one of two things. We can take the limit, actually one of three things. Limit as h goes to 0 of, we can say f of 2 plus h minus f of 2 all over h, all over h. That's option 1. You could take the limit as h goes to 0 of f of x plus h minus f of x all over h. That would give you f prime of x, and then plug in the 2 after that. And the third option is, we don't use this very often, but we could say this is our alternative definition of a derivative. The limit as x approaches 2 of f of x minus f of 2 all over x minus 2. So any one of those three would be considered using the definition of the derivative. So I'll just do the very first one, because we don't do that quite as often as the f of x plus h. So I'm going to take the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. So we're going to get the limit as h goes to 0. So f of 2 plus h is going to be 1 over 2 plus h plus 1 minus, if we plug in 2, we're going to get 1/3 all over h. And so we need to get a common denominator. So we're going to multiply top and bottom here by 3, top and bottom here by 2 plus h plus 1. So we're going to get 3 minus, now remember this negative must distribute over all that follows it. So it'll be a minus 2 minus h minus 1. And we're going to get our 3 times 2 plus h plus 1. And this divide by h is waiting in the wings as a 1 over h. Okay? So we get to the 3 minus 2 minus 1 all kill each other off. Once they are out of the picture, now we can cancel these h's, and then we can take our limit as h goes to 0. And so we have that negative 1 on top, and h goes to 0, so that's 3 times 2 plus 1 is 3 times 3 is 9. And that's our f prime of 2, using the definition of the derivative. All right. How about questions from homework? And there are, I should say too, if you're looking for more practice problems on the support, that extra video on the support materials, you'll see some a lot of limit and differentiability kind of questions worked out there. So that might be a good one to check out. Anything you'd like to see done?
I think we're good.
All right. So if we get, we got quite a bit to do here, so I don't know, but if we can get through it, I'll do some more practice problems at the end. But let's talk about extreme values of functions. So we'll talk about what do we mean by an absolute max, absolute min, or a global max, global min, same thing. So let f be a function with domain capital D. Let f be a function with domain capital D. Then we say that f of c is the, I'm going to say A, I'll talk about absolute max and absolute min. So it's the absolute maximum, which you will also see referred to as a global maximum. So different authors call it different things. You're equally likely to see either one of those used on an AP exam, or maybe even both. So the absolute maximum value of f on D if and only if f of c is greater than or equal to f of x for all x in that domain. So notice it says really clearly in the definition that an absolute maximum, a global maximum, is a y value. So it's the largest value of the function. Different than a relative maximum, which is going to be a point. So an absolute max and absolute min, the maximum, the minimum, is always that y value. So it's the largest one that appears. And it doesn't matter how many times it appears. So, you know, for example, we're talking about a sine curve, and the domain is all real numbers. You know, our sine curve does that wave forever and ever and ever. So the largest value the sine ever is 1. Now it occurs, you know, every 2 pi. So it occurs an infinite number of times, but it's still the largest y value. So we would say the maximum, or the global maximum, or the absolute maximum of sine x on the domain of all real numbers is 1. It's that y value. It doesn't have to be unique. I mean, it doesn't have to be unique in the sense that it occurs only once. There's only one maximum, or possibly none. And we'll talk about that too. So then the B, you know, then I think it's kind of clear. The absolute min, I'm going to be very brief. The absolute minimum, or global minimum, is going to be blah, 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 except that f of c is less than or equal to f of x for all x in the domain. So the global or absolute maximum is the largest y value that appears, and the global or absolute minimum is the smallest one. So if we think about it, whether and where a function has an absolute maximum or an absolute minimum depends on the function, its structure, but it also depends on the domain that we pick. So, for example, we talked about a sine curve. Domain is all real numbers. It has an absolute maximum, 1. It has an absolute minimum, -1. If we look at something like a parabola, so you say f of x is equal to x squared, we know that that is going to be our classic U-shaped graph. So the absolute minimum is 0. The absolute maximum is it doesn't have one because there is no largest value. So here it doesn't have a maximum because of the structure of the function. There just isn't the largest value. Okay, but that could also be based on the domain. So if we said, that we had f of x is equal to 2x, but we said the domain is going to be the open interval from, say, -1 to 1, then, we would get our straight line, y-intercept the origin, slope 2, and, it would be this line, except that because we don't include the endpoints, we would get something that looks like this. Now, does it have an absolute maximum? No. Does that make sense? Does it have an absolute minimum? No. And that's more an imposition of the domain. So the question comes up, what do you need, what conditions do you need to guarantee that a function will have an absolute maximum and an absolute minimum? Okay, on that interval, and I think more than just defined, but that's progress. This is one of our big name theorems. Okay, you can chew on that. We'll see if you can think on it. So this is the extreme value theorem. Extreme value theorem, which very unimaginatively is abbreviated to EVT. So what do you think we need? Yeah. What must be true about f? You said it's got to be defined, but more than even just defined, continuous. Yeah, we don't need differentiability because corners and cusps and vertical tangents aren't an issue. But we do need continuity, right? Because, if you think about it, if we had something like this, and we chose our domain to be there, we got a problem. There's not going to be an absolute maximum. What's getting in the way is that whole continuity thing. Okay, so if f is continuous, that's one of our conditions to guarantee that we're going to get an absolute maximum and an absolute minimum. What else do we need? What must be true about the domain, the interval? Okay, we said this does not have an absolute maximum, absolute minimum. We need the domain to be closed. Okay, so if f is continuous on a closed interval, A, B with our brackets, that's it. Then f has both an absolute maximum and an absolute minimum. Now, it doesn't mean that if we don't have these conditions that we can't have an absolute maximum min. We saw a sine curve on the open interval -infinity to infinity. It still has an absolute max and absolute min. You could have a discontinuous function. You could think of an example of a discontinuous function that would still have an absolute maximum and an absolute minimum. So, but to guarantee that we're going to get an absolute maximum min, we need to know the function is both continuous and on a closed interval. Okay, and so it leads to our candidate test, right? But before I do that, let's talk about relative mins and relative maxes. Now, if there is an absolute maximum or minimum, and we meet these criteria, so we meet these criteria, it is continuous, and it is a closed interval, where can the absolute max and the absolute min occur? So, we could do something, like that. And where could an absolute max or absolute min occur? Yeah, so it could be, someplace where we have a horizontal tangent, or perhaps some other undefined derivative, right? So a place where the derivative is 0 or undefined we call at a critical point. So we could have, you know, an absolute max or an absolute min that occurs somewhere where the derivative is 0 or undefined, or it could also occur at an endpoint. Okay, and so those are what we're going to look out for. Those are going to be, in our candidate test, those are going to be the candidates. We're going to find all the places where the derivative is 0 or undefined. We'll plug those values in along with the endpoints into the function and just pick out the biggest or smallest value. So that's where we're headed. Well, let's talk a little bit about our relative mins and maxes. So, our definition. So a relative, or some books or authors like to call it a local max or min, so let's talk about that. So let's see. So first we'll talk about the interior points. Let's C be an interior point of F. Then we say the point C, comma, F of C is a relative or local maximum if F of C is greater than or equal to F of X for all X in an open interval containing C. So a relative maximum does not claim to be the largest y value of the whole function. It's not the highest mountain in the mountain range. It's just one of the peaks in the range. So, you know, the idea is if you have a function that does something like that, then any point in here is going to have the largest y value, at least in some little region around there. And that qualifies to be an absolute maximum. And so then, or not absolute, a relative maximum. And so a relative min is going to look the same, except that F of C, so I'm going to say dot, 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 but F of C is going to be less than or equal to F of X for some open interval containing X equals C. Now, different authors of different books will say that an endpoint can or cannot be a relative min or relative max. So it just depends on the book that you happen to be in. On the AP exam, they understand that they'll never ask you if an endpoint on an interval is a relative max or relative min, because different students will have different answers depending on which textbook they're working out of. Our textbook does consider these to be potential relative mins and relative maxes. And so then instead of being, you just change the language, instead of an open interval containing C, which in mathematical terms means you got to have X values on either side of it. You just change it to an open interval on one side that we need to. So this, because it's the largest Y value in this region over here on the left where it's defined, that's going to qualify as a relative maximum. And likewise, this is the smallest Y value on some interval on the right that contains this endpoint, and so therefore it's going to be a relative minimum. And these are going to be named as ordered pairs. I think we're pretty familiar with that. So let's talk about our candidate test. I don't know why this is always a hard idea, but it is. Candidate test for, I'm going to say, absolute extrema. So what we do is find all the critical points on the domain. Okay, where's the derivative 0? Where's the derivative undefined? F prime of x equals 0 or f prime of x undefined. So you find those x values. Take the derivative, set it equal to 0, solve it. Then you just plug in the CPs and the endpoints back into the original function f. Not into the derivative, but into the original function. And then you just pick out the biggest one. So the largest y value is the absolute max, and the smallest is the absolute min. That's our candidate test. And when you oftentimes on an AP test question and on my test questions be asked to justify. So if you do the candidate test, that is your justification. So you find the critical points, you plug them into the original function along with the endpoints. The largest one's the max, the smallest one's the min. It's been justified because of the candidate test. Of course, where it really gets tricky is where you don't have a closed interval. And then you can't plug in the endpoints. And that's the part where it gets a little bit dicier. Let's look at an example here. Try to pick one that's got a piecewise function. Those are more challenging. I think we need a challenge in our life. So f of x is going to be defined as this piecewise function, 5 minus 2x squared. 5 minus 2x squared for x less than 1, and x plus 2 for x greater than, first one should be less or equal to, this is strictly greater than 1. So can we find, let's say find any relative extremum. So we're going to do that first. Find any relative extremum. Does that make sense? Ready to get up out of your chair and try to hit the board? Just a word of caution, so or maybe suggestion. So you got these two pieces. You have to consider each one independently. Is there any critical points in there? Is there any critical points in there? Is it going to be relative min or max? Where do they come together matters too. Because do they come together and is that a relative min or max? Do they miss? Could one of those be a relative min or relative max? So you have to give special thought and consideration to this boundary point there. Okay, I'm going to pause it so we can do this. Give it a shot. Explain this for the video. So what we have is on the left branch here, we have 5 minus 2x squared. And so if we take this derivative, then we're going to get a negative 4x and set it equal to 0. We'll get x equals 0 is a critical point. That is on the domain because that's part of where x is less than or equal to 1. So then we can do our number line and we can put in f prime and there's 0. To the left, if we plug in a negative, say a negative 1, then this is going to be positive. If I plug in, say, a positive 1, then, oh, I can't do that now. I got to, oh yeah, I can. So, but I can only go to 1, so only try to put in like a half. So that's in between 0 and where I cut this off. So at a half squared is a fourth. 2 times a fourth is negative a half. That's going to be positive. Did I do that right? I don't think I did.
The left side's going to be negative. No, you're plugging it into the f prime. You're plugging it into f.
Ah, plugging into f. Thank you.
Yes, to the left.
So, right. So I plug in something negative here, that's positive. I plug in a small positive there, that's negative. So there is going to be a relative max at 0, 5, right? Because plugging in 0 here is 5. Now, this function is continuous because when you plug in 1, you get 5 on the left. When you plug in 1 here, sorry, you plug in 1, you get 3, and plug in 1, you get 3. So they are going to connect. And we can see that our derivative, so our left-hand, let me do our number line. So there's 1. So the derivative on the left is our negative 4x. And if you plug in something a little bit to the left of 1, say 0, not 0, how about say 1/2, then this is going to be negative. The derivative on the right is always 1, so always positive. So there's also a relative minimum at 1, comma, and it gives us the same thing, 3. So relative maximum at 0.5, relative minimum at 1.3. Okay, that's good. Let's go on and we'll talk about the mean value theorem.
That's it. Get it back down.
That's what I hate about geometry. You have such a bad picture and then say they're equal. And
They're equal.
That's all I do irritates me.
Oh, so you can erase your stuff.
Oh yeah, I forgot to erase Larry. Sorry, Larry.
So another big theorem, mean value theorem, abbreviated
Oh,
MVT. Remember this one?
Yeah, I hate it.
I just remember that I don't remember what it is.
Well, that's something anyway, I guess. So if f of x is continuous, so if f is continuous, and I'm told that they're going to get even pickier about the conditions. So this is one of the really, really probably top 3 theorems in calculus. So they're going to be even pickier about the conditions because it says if f is continuous on the closed interval from a to b, let me write out closed, on the closed interval a to b, and differentiable on the open interval a to b, so not necessarily at the endpoints. Then there is at least one x equal to c in that interval from a to b such that our punchline is, remember? Prime of c is equal to, so the instantaneous rate of change is equal to the average rate of change.
Oh, yeah. I always hated this one because I felt like it was just an unnecessary theorem.
True. But it's used in the proof of the fundamental theorem of calculus. I think that gives it great weight.
So the FTC, the IVT, and the MVT, it is the 3 tier thing about that most important.
FTC, IVT, MVT, and then of course the fundamental theorem of calculus.
Well, that's what the FTC was.
Oh yeah, I'm sorry. Yep, from the FTC.
I was like, wait, what's
So
the
no,
second one?
we're missing one. FTC,
There was another.
yeah, intermediate value theorem, IVT, extreme value theorem is the other one, EVT. Yeah. Okay. So, I want to do an example of that. So let's try one here. Now, I'm just going to throw in here, then Roll gets his name. And what?
Oh, wait, yeah. This is the theorem for
It's all about timing. So Roll's theorem is like almost exactly the same as the mean value theorem. So again, you say if f is continuous on the closed interval a to b and differentiable, I'm being brief here, on the open interval a to b, and you add in f of a equals f of b equal to 0, then, so you think for a minute and you say, if we know the mean value theorem is this, and then you say, now f of b and f of a have to be equal to each other, then prime of c must be 0. And for that, you get your name on a theorem. I'll tell you what, standards were low that year. Roll must have had some money. He had some cash to get his name on that. That's the only thing I can come up with. Okay. So, can you show the mean value theorem applies to f of x equals x squared minus 2x plus 3 on the interval from -2 to 2.
Let's do that on the board.
Yeah, I think we can do this on the board.
Shall mean value.
Shall. The new Viking Titan.
So can we just say it's continuous because it's a, what are they called?
It's a whatever you, I love when you talk technical
It's
like that.
polynomial.
Polynomial, yeah.
Yes.
So you get, yeah, and you get continuity and differentiability both from that.
Yes.
So can you just say f of x is polynomial, and then you have to say so it's continuous? And
You have to say, yeah. So they want to know that you understand the
Can you just
conditions
say,
are
so
continuity.
it is differentiable and then that implies continuity?
Well, I mean, I think you need to say them both.
Okay.
Because that came up in the past, and what they said on the grading of this, if it doesn't say it's continuous and differentiable in the actual words of the problem, then it can't be assumed. So if it said it was differentiable, you would still have to say it is continuous either because it's a polynomial or continuous because it's differentiable. So that's kind of they upped the standard a little bit just recently.
I'll get it through the thing. What do you do in negative first?
It's
Negative
f
2 is
of
a,
b minus f of a.
wait, it's f of b minus f
Or is it f of a
I did
minus
wrong.
f of a?
I
No.
did wrong. Right, it is f of b?
Is it f of b minus f of a?
F b minus f of a
Over
will
b
be
minus a? Said it backwards.
Yeah.
But it should be the same.
No,
No,
because
it's
the
a
negative
negative.
2 will cancel this out. So that'll be a.
Subtraction. Because,
Well, I just do negative here, positive here,
yeah, then
and
it,
then positive here, positive here, so it's just over 4. It's gonna be negative 12 plus 9, so it's just gonna be
Yeah,
negative, it's gonna be the same
you
thing.
get the same thing, as long as you stay consistent with which
Yeah.
one you lead
It's
with.
the same thing.
Also, my guy is 11 and 12.
Yeah, you're right. Okay, fair enough. Touche.
Negative 2. So you put the f minus.
So if you do f of a minus f of b, will they mark you off? on the
No,
test?
no,
Okay.
you're fine. You're fine. But if you do f of a minus f of b, you have to do a minus b on the bottom. So it'll be the same. It'll be okay. Good.
on the AP test, I just showed, seeing how to work. Like every single step.
Do you?
Would be proud of us.
I wish I could get that on my test.
I don't know about that.
I might actually get some points back if I did.
Oh, we have to go back and confirm that.
Yep.
like high risk, high reward. Save time.
That's true, that is true.
Save time, but
High risk, high reward, I like that.
So you said, because
Oh,
we're not in
I
emergency.
Yeah.
So will they have a solve perceive on those? No, okay.
Probably.
Well, really?
So we did. Did
Oh.
you do that? Did you take the derivative, set it equal to?
Yeah, I did. Is that?
That's the
that is
C.
Okay.
Yeah, that's the C. You did it.
oh, no need to write zeros on it.
Looks like an alpha, my dude.
I didn't. I told you, once it gets down here, it's below.
Yeah.
It's below your.
Shoulder level. Okay, let me just, we're good. There's a couple more things. You can check the supplemental video if you need to. I'm just going to state that, because we're about out of time, but just the increasing, definition of increasing. So f is increasing it on an interval. On an interval. If for all x1 less than x sub 2, f of x sub 1 is less than f of x sub 2. So it just has to rise from left to right. So the idea is the definition of increasing and decreasing does not have anything to do with the derivative. We use the derivative to determine where it's increasing and decreasing. But we will include the endpoints on increasing, decreasing intervals unless the function is not defined. Otherwise, we will include it. That's the big thing.